Hello Laurier Shads. In today's video, we're going to look at how to set the center of gravity on the airplane so that it flies properly for our flight tests. A simple way to understand how an airplane works is that it basically hangs from a low pressure area on the top of the wing called the center of lift. So if that low pressure area is in a spot where there's more weight behind it than there is in front of it, the airplane will want to climb all the time. If it's the other way and there's more weight ahead of it than behind it, it's going to want to dive all the time. If the center of lift is right at the center of gravity, then the airplane will just continue on whatever path it's on. It won't want to dive or climb. And that's what we're looking for. So what we're doing during this test is we're trying to figure out where on the wing, front to back, this center of lift is so that we can match it up with the center of gravity of the airplane. We launched the plane level, but it arcs downward. That means that this plane is currently nose heavy. To fix this, we move the wing forward. This moves the center of lift forward, putting more weight behind it. This time when we launch the plane again fairly level, it's going to arc upward and then lose its momentum, stop, and kind of fall from the sky. This is a symptom of being tail heavy. To fix this tail heaviness, what we're going to do is we're going to move the wing back a little bit. It's a good idea to measure the distance between the nose block and the front of the wing adapter. That way you've got notes in your book on what worked and what didn't work and how well it worked. You can also use these notes to get the wing back where you'd had it earlier when it shifts from a hard landing. This time around, the plane will rise slightly, just a little bit, and then settle into a pretty nice glide. So that means that we're getting really close. We're just a hair tail heavy still. We want the airplane to go in a glide that runs at a pretty straight line and just continues along that angle until it either runs out of altitude or runs out of speed. Now you can see from the graph here that straight across is actually perfect, but the problem is it's going to eventually run out of speed and then just drop because the wing needs air going over it to create lift. By going on a slight downward slope, we trade potential energy, which is height, for kinetic energy, which is forward motion. So the amount of kinetic energy we're capturing from trading away the height should exactly equal the amount of drag that we have to overcome to maintain flying speed. If the glide is too steep, the airplane will accelerate. If the glide is too shallow, the airplane will decelerate until it no longer has enough speed to maintain flight. It's going to take a fair bit of measuring and flying to get this perfect. Once you do, you can either mark it on the fuselage in pencil like we're doing here, or you could even take a little piece of scrap balsa, cut it to the width of the fuselage, and then just glue it so that all you have to do is slide the wing block forward into it each time that you're going to fly. Once you've got the plane balanced so that it's flying ideally, you want to go back to the wing, balance the airplane on your fingertips on the wing, and determine where the center of gravity is on the wing, because that'll correspond to your center of lift. That's going to come in handy to know when we start adding weights to this plane later on, because we're going to have to rebalance it each time.